Okay, thank you. So this talk is based on the observation or opinion, if you like, that many problems which we face when we, in quantum field theory and in particular in quantum gravity, can be traced back to the very way in which we constructed quantum field theory and in which we understand it, namely the canonical Hamiltonian formalism. From this point of view, it is rather surprising that the fact that there are many different Hamiltonizations of field theories given by the multidimensional variational problems, which are known to mathematicians, and only one of them is used as a basis of quantization, namely the canonical Hamiltonian formalism, which requires space-time decomposition. All other Hamiltonizations do not require space-time decomposition, and in fact they allow to formulate dynamics as in terms of the cross-sections of the finite dimensional bundles. That is the analog of the configuration space in such alternative Hamiltonizations is finite dimensional, and as I told, all space-time variables are treated on the equal footing. So the simplest example of such Hamiltonization is the so-called de Donderweil theory. We have Lagrangian function, which is function of field variables, first derivatives of fields and space-time variables. We define polymomenta as analogous of canonical momenta with respect to each space-time derivative of fields. And we define the so-called de Donderweil Hamiltonian function in this way, which will be a function of what I call polymomenta of phase space, the space of field variables phi, polymomenta pi, mu, and space-time variables, which will be treated as analogs of time, as a multidimensional analog of time. And then in terms of those variables, we can write the Lagrange field equations in such space-time symmetric, space-time symmetric Hamiltonian-like form, provided the following regularity condition is fulfilled, which is, for example, fulfilled for the number Goto string. So as we see, then the classical field solutions are cross-sections in the finite dimensional bundles over the space-time. Namely, that would be the finite dimensional space replacing configuration space, and that would be our analog of the phase space. So we would like to investigate if such a framework would be used as a starting point of quantization. That was actually asked already by Weil in 1935, but because the brackets were not known, so nobody was able to do this. So I was able to find brackets. So before we start quantization, I have to make the hardest part of the talk, namely to review what are the mathematical structures which are suitable for constructing quantization. Usually the Poisson brackets are constructed using the symplectic two forms. In this framework of field theory, we have form of degree n+1 in n-dimensional field theory. I call it polysymplectic. It allows us to establish map between horizontal forms, which will be representing dynamical variables, and multivector fields. So I think most of you know that there is similar map between functions and Hamiltonian vector fields, which allow us to define Poisson brackets geometrically. And then using this map, we can define the following Poisson bracket, which is easy to show is graded Lie bracket. And also in careful investigation of this map allows to see that the space of forms for which this mapping is possible is not closed with respect to the exterior product, but it is closed with respect to what I call co-exterior product, so it produces form of degree p plus q minus n, and it is graded commutative. So as a generalization of the Poisson bracket structure to this framework, the Donderweil framework, we have the structure which is known as Gerstenhaber algebra. Moreover, this construction allows us to write the equations of motion in terms of the brackets with the de Donner-Weil Hamiltonian function. So the bracket with the Donner-Weil Hamiltonian function will produce the coexisting differential, which is like the generation of the total time derivative by the bracket with the Hamiltonian in mechanics. And we can also identify the canonically conjugate variables in this framework. Namely, we can calculate bracket between field variables and such forms of degree n-1 constructed from the polymomenta, and also some other combinations which are very simple, which are like the canonical brackets in mechanics. We can also extend the geometric pre-quantization to this formula, to this framework, and actually within pre-quantization framework, we can see that we, in order to normalize pre-quantum wave functions, which will be non-homogeneous forms, we have to introduce metric structure on the space-time. So metric structure appears as a consequence of quantum normalizability. And then the algebra of forms becomes Clifford algebra. So the simplest way to see, another way to see how Clifford algebra appears is to consider this bracket, to try to quantize it, if everybody can do it. And because of this delta symbol here, delta mu, we naturally arrive to the representation which uses Dirac matrices. So this will be the quantum representation of polymomenta in terms of partial derivatives with respect to the field variables. And this will be a representation of the basic form. I think I have not explained the notation that omega is volume form of the space-time, so it is form only n. And omega mu is its contraction with d mu. Okay. So if we represent those forms by Clifford algebra elements, because the later are dimensionless, obviously, we need to introduce a scale, which is kind of 1 over kappa, like a fundamental volume, a minimal volume. So this comes as part of the procedure of precanonical quantization. And because we have seen that on the classical level, Poisson bracket with the Donner-Weil Hamiltonian generates exterior differential. So after Cliffordization, it is natural to expect that we, instead of IDT, in this framework, we have something like Dirac operator. And for dimensional reasons, this constant kappa appears here. So this is kind of the framework which can be constructed. And for the free scalar field, we obtain such expression of the Donner-Weil Hamiltonian. So interesting properties of this framework is that obviously we have the conserved current. The wave function itself is Clifford algebra valued. It is functional of our analog of the configuration space, as it should be in quantum theory. Namely, yes, space of fields and space-time variables. We can show that Ehrenfest theorem is fulfilled by this equation, namely Donner-Weil Hamiltonian equations, or classical field equations can be reproduced as equations of expectation values as a consequence of this quantization, this analog of the Schrödinger equation, and the obtained expression of the Hamiltonian. So if we quantize free scalar field in this way, we can easily reproduce the spectrum of free particles. We can obtain the ground state and actually all excited states for the free field theory. We can define such transition from phi, which is like Schrödinger representation in our framework, to phi of x, where pi mu is translation operator, which we obtain from rewriting the precanonical Schrödinger equation in this form, which is not difficult to do. And then by always repeating literally the known Lemon-Chemin representation calculation, we obtain the correlation function. That is, the free field theory is reproduced without trouble with the additional advantage that in the Lehmann-Cherin representation, nobody knows what is phi of 0. It is formal expression. It is value of operator value distribution at a point. And here we have just phi, which is our field coordinate. So this calculation much more sensible in this framework. Moreover, I will intrigue you by saying that if we make calculations in lambda phi 4 theory, then all loop diagrams will be certain expressions involving degrees of kappa instead of diverging loop integrals. Okay, so of course you are not happy now because you don't believe me that you can reproduce quantum field theory in such a framework, that you can use partial differential equations instead of functional derivative equations, or instead of operators, so whatever. We are all studying at the university. So of course you want to know how the standard description, let's say, of the scalar field theory in terms of the functional Schrödinger representation and variational derivative equations would be related to this description in terms of the multi-temporal Dirac-like generalization of the Schrödinger equation, which doesn't need space-time decomposition, and such expression of the Hamiltonian, the Donner-Weil Hamiltonian operator. So I could explain that in more details, but for the lack of time, I just present the expression, and everybody can ask me later how it was obtained. It is a result of two papers. One of them is published in Advanced Theoretical Mathematical Physics. Second one is still under consideration. Okay, so more or less the point is that you can take pre-quantum wave function restricted to the surface phi of x and make the operation which is known in mathematics as Volterra product integral. And you can argue that this expression makes, you can even interpret physically what it means, using the probabilistic interpretation of pre-canonical wave function and the Schrödinger function. Also, this expression is valid only under such limiting transition, namely the parameter kappa, which we introduced as kind of ultraviolet scale, when it goes to delta of 0. So, in this
if
sense,
I now recompute the commutation rule, ETCR, for the field phi with a finite volume element, what do I get? Do I get Dirac-Kaplan?
oh, it's not so straightforward, and I'm really limited in time. Ask me later, please. I can easily reproduce equal time commutation relation, but I will not so easily reproduce not equal time commutation relation that you would immediately understand.
Okay.
So the message from this relationship between pre-canonical Schrödinger equation and the functional derivative canonical Schrödinger equation is that the theory which we get from canonical quantization appears to be a limiting case of the procedure of the theory which we obtained from pre-canonical quantization. This is the limiting procedure, or what one can also equivalently write as 1 over kappa. Beta goes to the spatial volume element.
Is this also the reason for renormalization, that you have to regularize delta 0 in the usual one?
In the conclusions, I will write that the theory which we obtain this way is already regularized if you use the wording of Wheeler, but it is not renormalized. Renormalization will mean that you want to get rid of this scale kappa, and it will not work in quantum gravity. Okay, so now to some extent we are prepared to quantize gravity using this framework. So we start from the standard field by Lagrangian. We treat field by variables and spin connection variables as independent using the Palatini framework. We define polymomenta associated with spin connection and polymomenta associated with field binds. We define how the Donner-Weil Hamiltonian function will be given by this expression. And what we see that because polymomental spin connections are related to field binds, so our polymomental phase space is constrained here. So we need to generalize to the framework of the Dondler-Weil some elements of the theory of constraints, which I have done. The main idea is that, of course, usually our constraints are functions on the phase space. Here we have brackets defined with forms, so it is natural to expect that constraints are represented by certain forms, which I construct here. That using my techniques I can calculate brackets of those forms, and I see that extrapolating the terminology of Dirac, we have theory with second-class constraints, but of course those constraints have nothing to do with those which we know in the chemical treatment of general relativity, or at least I don't know how they will immediately relate. So we need to work further. Actually, we need to generalize the definition of Dirac bracket to this framework, which I have also done. So this is the definition, which involves it is so the inverse of the form representing constraints. It is a little bit tricky and can't be explained within a few minutes. But the end result is that if we calculate brackets between polymomenta and the field variables, then we get very simple expressions. This is what is not quite surprising. So we get more or less delta Kronecker here. And for the polymomenta and field bind variables, we get 0. So effectively, analysis of constraints excludes field binds from what would be then the framework of quantization. Okay? So now, equipped with those relatively simple brackets, we can perform quantization using our pre-canonical restrictions. So I will not even try to explain what is done, more or less because of some lucky constellation of circumstances, it is possible to go till the end. So one of the results is that the curved space gamma matrices are becoming operators expressed in terms of the partial derivatives with respect to the spin connection coefficients. And the same way we can construct the expression of the Dondler-Weil Hamiltonian operator.
What is lambda?
Sorry?
Lambda, what is lambda?
You mean big one, it is cosmological constant, which was in the original expression of the Lagrange, which I used to start the analysis of general relativity. And this is Einstein's gravitational constant. Okay. So we can also construct the, obviously we need covariant analysis of the Schrödinger equation, which we generalize our previous framework. So here gamma matrix already we have found that it is actually operator. So this is the expression of quantized Dirac operator, and this is the final form of the equation. For the wave function, Clifford algebra valid wave function of spin connection variables and space-time variables. Field binds are excluded by analysis of constraints. We can also construct Hilbert space, define scalar products, so we would expect some integration over all spin connection coefficients, which we want to be to have invariant measure. So this is the invariant measure which I propose based on the more or less repetition of the arguments by Misner in 57. Because it involves determinant of field binds, this will be operator valued measure. And there is one immediate consequence of this definition of the scalar product. Namely, we want, of course, wave functions to be normalized, to have finite norm, and it is only possible if psi's are going to 0 at infinite omega. And that means that quantum, theoretically, there is no wave function in the regions with infinite curvature, so to say. So the quantum gravity cures the singularity problem simply by construction in this case. So let us now go to the most interesting part. You have given 5 minutes more to the previous speaker.
I did.
Okay. So we start from the 4-dimensional flat space within the universe. We calculate spin connection coefficients. Only one component survives. This is how my precanonical Schrödinger equation will look in this case. It can be solved by separation of variables. We obtain wave function, and this is the distribution function of spin connection coefficients which we obtain. C constant depends on cosmological constant kappa, h, and Einstein's kappa. It is also depending from the ordering of operators which we assume. So this is kind of physical prediction of the theory within the cosmological framework. We have Levy type, or it is actually student distribution, with flat tails of the components of spin connection, which is like cosmological, quantum gravitational, spin connection, random field background. We predict non-Gaussian statistics for this, and we can immediately read some consequences from that. Namely, because so the shape of this distribution is like that. Rho of omega. So at very small values of omega, this can be imitated by Gaussian distribution. So when we interpret cosmological data in the regime of very small curvatures at large scales, so probably we will not be able to distinguish this non-Gaussian distribution from the Gaussian. But at the intermediate scales of the curvature, and especially at the higher curvatures, we have so-called distribution which has Levy tails that is known to be related to the fractal dimensionality of the trajectories. So essentially we predict that if we put test particle to move in such non-Gaussian distribution of spin connections, which are predicted by quantum gravity in this approach, so these test particles will feel something like fractional dimensionality of the space-time. So this is what we can expect. Okay. So I will not go to the main details, just if you allow me to finish with conclusions. So first of all, we have proposed some framework of quantization, which is based on the version of the Hamiltonian formula, which doesn't require space-time decomposition. We have argued that the standard quantum field theory based on canonical quantization can be viewed as a limiting case of what I call pre-canonical quantum field theory. When we apply this to the quantization of gravity, we obtain certain partial differential equation for the wave function of spin connection coefficient in space-time. One of the immediate consequences is that the quantum geometry will be described in terms of the transition amplitudes between one value of spin connection at one point and another value of spin connection at another point. So we can speak about space foam, spin connection foam, or if you like, quantum space-time turbulence, which is very close to the original intuitive ideas of Wheeler, I would say, much closer than the Wheeler's superspace formulation. Okay, so there is also an interesting observation that this combination of constants, actually, which we just kind of write equation is for, this combination of constant is dimensionless, and it is generated more or less by reordering of the operators. I can even make estimation of that based on the number of the spin connection coefficients. So this coefficient should have order of degree n to degree 6, n as dimension of space-time. So if we can try to estimate the value of kappa from that, and we obtain value about of subnuclear scale. which is slightly disappointing and strange. If, however, we just assume that kappa is Planckian, then we obtain the error in the estimation of the cosmological constant, which is the standard 120 orders of magnitude. So this is additional reason, this is additional evidence that what is introduced as kappa has something to do with the cutoff in the quantum theory.
Is this function psi, which is just satisfies the Schrödinger equation, is it functional?
It is functional.
Functional.
It is functional, which can be related to the Schrödinger functional, but rather complicated construction.
Yes, all times.
So omega in his case is not a function.
Yeah, it is just coordinate in which connections take values. Okay, so that far. We can also argue that this precanonical Schrödinger equation for quantum gravity can be understood as a multidimensional matrix analog of the Kummer-Geometric equation, which can be analyzed, and actually this behavior of the distribution function, you can just show that more or less it is very generic property. Of course, coefficients will be different, many things will be different, but the Levy tail at the Planck scale is the thing which will prevail, and at the zero it can be cups or it can be Gaussian-like. So I think, and just last thing, the construction leads to the non-perturbative construction by just how it is done. It is manifestly generally covariant. It is background independent in a certain sense. It is mathematically much better defined as any infinite dimensional formulation probably would ever be. It can work any number of dimensions and any signature. The problem will be with interpretation of the wave function in arbitrary signature. And it doesn't include the MSD parameter. I can do it with MSD if I want, but I don't need to. And also metric structure becomes emergent. This is the explicit expression of the metric tangibility in the scope formulation. Thank you very much.
Questions?
How did you account for Lorentz invariance? I mean, you speak of connection, but how do you impose the invariance of the Lorentz distribution in this framework?
You mean local Lorentz invariance?
Yeah.
This is kind of, I told you about manifest general covariance. About Lorentz invariance, it seems, but I don't have finished proof yet, that the equation which I have derived for the Clifford-Valid wave function of this space of spin connection and x space-time is actually equation of parallel transport of the Clifford algebra value function in this space, if cosmological constant is zero. So in this sense, this is kind of rephrasal of your question, because if it is parallel transport of this space, means that local invariance is taken into account. But if you ask me in some arbitrary place, maybe I will have difficulties to demonstrate it. But because it is parallel transport, if cosmological constant is zero, so it is done. It was not trivial to see.
Okay, so since time is quite advanced, let's thank the speaker again.